Easy? Oh, the tutorial part. That was easy. Paper you liked less? All right. So let's pick up where we left off last time, and we'll swing back around and look at that Hello World program later on today. I need to make sure I give you enough stuff to be able to do your homework assignment tonight, and we can get out a little early, great, but I tend to get long-winded, so we'll see, see what happens. All right. So if you remember back early on in this slide set, we talked about how human beings solve problems. Okay, we use our memory. That's how we remember things like our name and our phone number and stuff like that. We like to ask questions, and we use repetition. We were talking about bumping into walls and that kind of crap last time. Okay, so this is how human beings solve problems. Well, then we talked about programming languages and what the job of a programming language is. So it's attempting to mimic the way people solve problems. So it has to give us constructs built into this language that allows us to solve problems in a similar way how we solve problems in real life, through our memory, asking questions, and repetition. Okay? So we talked about last time the mapping. Memory, the human memory in a programming language is mapped through something called variables. So it's mimicked through a tool called variables, and we'll start talking about that today. Asking questions is mimicked through something called conditionals or if statements, and repetition is mimicked through loops. Okay, then we went through all these slides about 3 types of languages: machine, low, high, 2 types of languages, interpreted and compiled, domain-specific versus general purpose, functional, procedural, object-oriented, loosely typed versus strongly typed. Okay, and we'll come back to this here in a few minutes when we start talking about variables. Then we talked a little bit about the history of these languages. This is C# to Java to Objective-C, what I call the big 3. Kind of the history of these guys, how they came to be. We did talk about Java and Microsoft's lawsuit, right? Okay, and kind of how we got to C#. We talked about how the Java virtual machine allows us to do platform-independent programming, right? Because they ported the Java virtual machine to various platforms. And we talked about how C# claims to be platform-independent as long as you're running it on Windows. Okay? But Java did learn a little something from this just-in-time compiler thing here, which does make C# significantly higher performance because actually at runtime, the program is running natively on the CPU. Where Java, at runtime, the program was always running through an interpreter that was switching between the virtual machine and the real machine. So Java took a play out of C#'s book and incorporated just-in-time compilers as at least part of that problem. So some parts of the solution could be mapped to actual CPU instructions prior to runtime. The rest of them were interpreted at runtime. So we could say that maybe the Java today is actually Java 2.0. We learned a couple of lessons from C#. Okay, now one last thing I want to throw in here that's kind of a perk of C# and the .NET languages. Maybe it kind of goes on this slide up here, the big 3. When you say C#, you can also say just the .NET languages. Okay, the .NET languages are C#. Let's put it in here. So we have Visual C++. We have C#. We have Visual Basic. And there's also an ASP.NET, which is kind of a competitor with PHP for web programming stuff. All right, so these are the .NET languages. Now, what's kind of nice about the .NET languages is, first of all, they are all programmed inside of a tool called Visual Studio. Okay, Visual Studio is something called an IDE, Integrated Development Environment. It's a text editor on steroids. All right, lets us, and we'll see an example today, and I'm sure some of you, when you did your tutorial for Hello World, probably used one of the Java IDEs called Eclipse. Okay, you might have used NetBeans, which is another IDE for Java. I would say Eclipse is probably the industry standard, but they're all the same crap. You know, they all do the same thing. And Objective-C, their IDE is called Xcode. So these are all the same kind of tools. But in any case, what's nice about the .NET languages, if you are writing software for Windows, is different parts of the product can be written in different core languages. So for instance, let's say you're making a video game. You can write the gaming portion of it in Visual C++, because maybe it needs to be really fast. You might have the interface part of it, like the user creation or the account creation or the login screen, things that are like lower performance. Like nobody brags about how many frames per second they were getting on the new user creation screen. You know what I mean? You know, so screens like that really are more functional to getting started with the game, maybe you write those in C#. And the reason why this is kind of a neat feature of the .NET languages is because no matter what the language is, whether it's C#, Visual C++, or Visual Basic, they all compile to Microsoft Intermediate Language. They all compile to missile code. So whether your starting point is C#, or Visual C++, or VB, any of those languages, when we send it through the .NET compiler, the output will be Microsoft Intermediate Language, missile code. Okay? So that means certain parts of our program we can write in one language, other parts we can write in another language, other parts we can write in another language. Now, that's probably not that common of a thing to do, but it can be done. It's an interesting little caveat to the .NET languages. It's entirely possible if you're doing something with networking in one of your projects that one of the tools has a library that was pre-built for it that you found online that you might be able to leverage to make your job a little easier. And if all you can find is a C++ library for networking, maybe you go ahead and use that and write the rest of your project in C#. Kind of a neat feature of .NET. All right, then we talked about why Java didn't die. So one of the big reasons is Google doesn't like Microsoft, right? And they used to like Apple, but they don't really like Apple anymore either. It's the whole iOS and Android. Yeah. I mean, and it really isn't a Microsoft's evil, Google's not. They're competitors, right? Microsoft and Google are competitors in a lot of different fronts. Now, search is a big deal, right? You have Google, and that's the big search guy, right? And then now you have Bing. But even outside of that, you had Google with their Google Apps, Google Docs, and you have Microsoft with Office. So they were competitors on a lot of fronts, Microsoft and Google. They also had very different philosophies. Early on, it seemed like Google and Apple were much more compatible companies philosophically. But as soon as you really had them competing on mobile platform, mobile OS, that probably ruined that relationship, at least reasonably well. Now you have Google kind of replacing Microsoft in the story of Microsoft versus Apple. So you had the old story, Apple versus Microsoft. Now you have Apple versus Google, right? Where Google's solving the old Microsoft problem, where they're writing a piece of software, Android, for 1,000 different computers, 1,000 different smartphones. Apple's writing their operating system for just their own stuff. So you have the proprietary guys versus the open platform guys. Interesting war. At the end of the day, us consumers benefit from it, right? We do. I think I asked last time how many of you were iPhone versus Android users, half and half-ish, whatever it was in this class. But had both of those guys not been there to compete with each other, we wouldn't be running around with the cool technology we have, regardless of which platform you've chosen. Any of you still using a flip phone? My neighbor still uses a flip phone. My mother-in-law had a smartphone, couldn't run it. Switched back to a flip phone. But my grandmother uses an iPhone now and is better at it than my mom. We just lost my grandpa a couple months ago or something like that. He was very old. But so now she is having to do a lot of stuff on her own. So she's trying to learn how to use an iPhone, and she's like 90. She's better at it than my mom by a lot. My wife keeps getting impressed about some of the things my grandma sends her. My grandma's texting her and sending her pictures and stuff. Before long, she'll be tweeting. It'll be interesting. But, technology really is interesting because it has opened the doors to a lot of different people. I would say that an iPhone makes more sense for grandma than an Android device. Even if you're an Android fan. Get into less trouble. All right, so Java didn't die. Big reason is Google. Google propped them up because they were a Google shop, or a Java shop, rather. From a technology perspective, the biggest reason, I believe, was the Java applet. It was there since day one. It was built into HTML. HTML since day one has had an applet tag for embedding Java programs within your websites. And it's heavily, heavily used in the financial markets for stock trading tools, professional stock trading tools that launch out of websites. It's a big deal. Microsoft tried to copy it with COM and Activex. It never worked out. And the thing is, you look back and you say Sun made applets a long time ago. Couldn't Microsoft duplicate it? Sure, but Microsoft is solving a difficult problem. On one hand, they don't want to hurt. Well, on one hand, they don't want to help their competitor, right? So they can't really make their stuff for other people's stuff, which is why when you go to a page that says it requires Microsoft Internet Explorer that has an ActiveX control, if you're running Internet Explorer, you're happy. If you're not, you're ticked off, especially if you're on a Mac, because that means you can't go to that web page. Microsoft's okay with that because if you really want to go to the web page, now you have to buy Windows and install it on that Mac and then dual boot into Windows and then you'll have Internet Explorer. So Microsoft likes that path because they get some money out of it. So they were really forced to create ActiveX within their own ecosystem, which comes with its own caveats. I don't remember if I asked this question last time or not, but how many of you in here, your favorite browser is Internet Explorer? You use Internet Explorer a lot, even on your Mac? Yeah. So, but Windows side of the Mac, right? Yeah. Okay. No, actually Safari, but I have another laptop. I use Internet Explorer. Okay, on the Windows side. Okay. Let's see. So PC users, I'm going to guess your favorite browser. I'm going to say Chrome, probably number one. Firefox 2. Any Opera users in here? I'm going to say 1 or 0. That's 1 or 0. Okay, those are your big guys on the PC for technical people, technical folks. On Apple, number 1 is probably Safari. Safari is to Apple as Internet Explorer is to Mac. Is to PC or to Windows. Although I would say Safari is the better product. Having said that, I think Chrome is a big win on Mac, and Firefox too. So really, if you were going to use one browser and you wanted to work on everything, Chrome is probably a pretty good pick. Secondarily, Firefox. So kind of an interesting thing there. An interesting kind of fact is that Internet Explorer is still the most popular browser.
I think I don't hate it. I just don't like using it every day.
We don't like Microsoft. It's funny, even as technologists, when you hear Microsoft, don't you kind of doesn't it just have a negative connotation? And we don't know where it came from. Microsoft isn't like extra bad.
I think it's like government.
Yeah, all these companies are the same type of corrupt. They all make a lot of money off us.
It's not just about Microsoft, but for example, as a web programmer, always Chrome and Firefox support the last version of CSS, support the code path. Internet Explorer years just to support what other browsers. It's very slow.
Okay. So from a developer perspective, you feel that Internet Explorer is difficult to support. So you would prefer them not exist because it would make your job easier and probably allow you to produce higher quality sites. Because now your sites have to be bloated because you have to have one interface for everybody else. And realistically, at least Safari and Chrome should be almost identical because they're both WebKit based. Firefox almost is now. You might have to make a couple of changes for Firefox to make certain things work. But Internet Explorer is totally a different product. So I could see that. But certainly, in terms of your audience size, though, Internet Explorer has the largest audience. Why? Well, the guy at Best Buy told Grandma to double-click on the blue E. That's where the internet lives, right? Okay. I'm a huge advocate of the right tool for the job, and obviously I'm a big Mac fan, but like I think I explained last time, it's because I can run all platforms in this one machine. So I do a lot of programming in Windows. I do programming in Mac. I'm a Linux user too. It's the right tool for the job. There's nothing wrong with Microsoft. In fact, when you really think about it, Windows is shockingly good today. You know, when you have your, let's say Windows 8 needs some work, but from a stability perspective, Windows 8 is pretty solid. Windows 7 is a great operating system. I mean, it's stable. And it's made to run on a million different configurations of computers. That's a technological marvel, how good that operating system is. I mean, fine, the Mac OS just works. Well, you designed it for 6 machines. Okay, no wonder it works. So, yeah, Microsoft has some of the smartest people in the world working for them, and you know, I tend to defend them when it comes to certain things because they are playing, what is it, like the superhero thing? With great power comes great responsibility. In the Activex days, Microsoft was the most powerful company in the world. The biggest. I mean, they were the biggest target. If somebody was writing viruses or something like that, Microsoft was their target. So they were under this microscope. And when they had to write Activex, they had to write it in terms of what would work well with their software because they were proprietary in that they couldn't help their competitors. They were playing this weird game. Okay, they had to make some choices that maybe logically didn't make sense from a technology perspective, but had to make sense from a business perspective. So they were forced into making certain decisions. And because of that, Activex really never got adopted, except for from the die-hard Microsoft shops. Places just did everything for Internet Explorer. In the early days, it looked like it was going to be Internet Explorer versus maybe Netscape or something like that, but Internet Explorer really owned the market. So a lot of people got on board then. But now, I mean, certainly in the technology industry, we look at Chrome and Firefox as legitimate competitors, right? You know, in fact, among technology people, you would say Chrome and Firefox are better browsers than Internet Explorer. Okay? And where, you know, your casual user might not necessarily know about Chrome or Firefox unless, you know, somebody else put it on their machine and you tell them to double click on the wacky looking bird instead of the blue E. Right? So, interesting stuff, that world. So Activex, anyways, had a lot of security holes, not because it was poorly written, but because they were forced to write it for a platform that already had some security holes in it because they had a big audience of people trying to break it. Nature of the beast. But anyways, that kept Java alive. Okay? Finally, from a teaching perspective, I really like Java. You get all the benefits. Again, we're looking at our hierarchy here, the lineage of these languages. So in the early days, we had C. C++ used C syntax. So to move from C to C++ didn't require you to learn a brand new language, just a couple of little caveats. Go from C++ to Java, same thing. Java looks like C++. People complain that C# looked too much like Java after Microsoft tried to steal Java directly. It's not that C# looks like Java, it's that C# looks like C++. Okay? So these two languages are both based off the same parent language. Why? Because developers, if we expect developers to move over to this newer technology, they have to be able to make that leap easily. Does that make sense? If you're used to using product X and product Y has a technological advantage, but it has a huge learning curve, you might not jump over to product Y. Does that make sense? Okay. But if product Y is better and moving from product X to product Y isn't that huge of a deal, why wouldn't you move, right? Especially if it doesn't cost you anything. See, we should start bad-mouthing Google now. She's got the Google mug. You an Android user too?
Apple.
Apple user? So what's with the Google mug? Got it for free? Huh? Sure. Free mug. So I gotcha. When was that?
Oh gosh, over a year ago.
Oh, I do remember when he was back on campus. I'm still friends with him on Facebook. Okay, so in any case, that's why our languages today look a lot like the languages from yesteryear. I really like Java from a teaching perspective, not because Java is a better language than C#, but from a teacher's perspective, I don't have to worry about what kind of computers you have at home. You know, if you happen to, when you did your tutorial for the Hello World program, if you happen to use Eclipse, whether you did or didn't matter. We're going to be using Eclipse in here. Eclipse is available for Windows, for Mac, for Linux. So I don't have to support half of you on PC and some of you on Mac and a couple of you on Linux. It's all the same crap across the board. Java has that functionality, which makes it very, very good. Historically, there was a language that tried to be like that. It wasn't platform independent because everybody was using Windows back then, but there was a language designed for teaching called Pascal. Okay, yeah, and Pascal actually, then people liked it and they turned it into Microsoft. Good old Microsoft stole Pascal and called it Visual Fox Pro. That was Pascal syntax in a Microsoft package that probably cost $100 per license. But in any case, Pascal was originally designed specifically for being a teaching language. And then people were learning how to do it, so they started writing crap in it because that's what they knew, right? Well, if I'm teaching you Java, and I'll show you this today, the difference between Java and C#, itty bitty. Itty bitty. I could probably give you a functional Java program and have you try to compile it in C#, and you'd have significantly fewer errors than you think you should for these languages to be different languages. A lot of the things are like case sensitivity, like a lowercase s instead of a capital S and stuff like that. So learning Java is the same thing as learning C# in my opinion. Once you know one, you know the other. Objective-C looks a little bit more cryptic, but once you know these two, learning Objective-C isn't a huge jump. You're just dealing with a little bit different syntax feel, but your problem solving is already there. Okay, so let's talk about variables. Variables mimic, well, let's say this. These guys are named containers for holding values which mimic the way humans solve problems. Okay, that's what a variable is. Now I say a named container. So when we go back and we were talking about human beings using memory last class, I asked you, I said, do you know what your name is? So somewhere in your head, you have a little container that's labeled my name. A little piece of duct tape on it that says my name in a Sharpie, right? Okay, it says my name. And inside there you pull it out and says, oh, Mike, that's me. Make sense? Okay, that's what a variable is. Variable is a container, piece of duct tape on it, with a little name on it that tells you what's in that container. And then inside the container is the actual value. Okay? Now, jumping back to that, there's two kinds of programming languages right here. The last one of those. We have loosely typed and strongly typed languages. Loosely typed languages require, let me start with strongly typed. Strongly typed languages require that we not only name the container, but also write down what kind of thing that container is built to hold. Okay? So if you get a box for shoes to store shoes in, a strongly typed language makes you label it as a box for shoes, and then will only let you put shoes in there. You can't then go and repurpose it and decide you're going to store hangers. That make sense? Okay. Loosely typed languages let you have a box that's general purpose. Put whatever name on it you want. Hopefully the name gives you some information about what's in there. But what you put in the box is up to you, and it can change. You can put shoes in there today. Next week you can dump it out and throw hangers in there, whatever. Okay, so loosely typed languages don't require you to indicate when you first buy the box, don't require you to say what you're going to store in there. Strongly typed languages do. All right, now if we're putting some of our own keywords on here, like we did with interpreted versus compiled languages, typically we're going to think of strongly typed languages as relatively fast. We're going to think of loosely typed languages as relatively slow. And you notice the sentence we have right before that, many loosely typed languages are also interpreted languages. And on the interpreted slide, we said interpreted languages tend to be slower. Strongly typed, many strongly typed languages are also compiled languages. Compiled languages tend to be faster. Okay? Part of that reason is for a loosely typed language, at runtime there has to be this extra dude that's floating around called a type inference engine, which is a really fancy way of saying the guy who looks in the bucket to determine what's in there before you use the value. Okay, so if you have a container and the container is, let's say the container, you can't see through it. It's opaque. And the container might have shoes in it or might have hangers in it. Somebody has to look inside to see what's in there before you can use whatever's in there, so you know what's legal to do and what's not legal to do, right? Probably aren't going to put hangers on your feet. Okay? You're probably not going to use a shoe to hang a shirt up in the closet. Make sense? So if you're trying to do shirt hanging stuff with shoes, you misuse the variable. Make sense? You misuse the value in the variable. Loosely typed languages, while they allow you to store the value generically, they still check to see what the value is before they allow you to use it. There's a difference between storing it generically and using it generically. So they have to have an extra guy who checks before you're allowed to do stuff, which means slower. Make sense? But if you have a box that's labeled hangers, you could close your eyes and reach in and you know you're going to pull out a hanger. You don't need to double check to make sure it's a hanger. That's what that box was made to hold. Make sense? Those are your strongly typed languages. So strongly typed languages put the burden on the programmer. When we create that variable, we have to specify, I intend to store this in this container. And now we're stuck with it. Okay? So if we go to Target and we buy the box for hangers, if you need to store some shoes, go back to Target. Buy another box for shoes. Make sense? Loosely typed lets us repurpose. All right, so variables are named. I always do this. Why can't I spell container right the first time? It's really interesting. I bet you the last 10 times I've written that, I spelled container contained all 10 times. It's got to be a psychologist type thing somewhere in there. It's like a scratch in the record. What was it talking about? Oh, good. Okay. So name containers for holding values. Some of them are typed, some of them are not typed. Generic syntax for a variable. Type followed by variable name equals value, semicolon. Okay, this is the generic syntax for defining a variable in a strongly typed C-like language. So this little thing I have right here, this generic syntax, that is an accurate statement in any language you see on here. That's how you define variables in C, Objective-C, C++, Java, and C#. All the way down to the semicolon at the end. Exact same syntax. Okay? So, the type, followed by the var name, followed by the value. Now, what's a type? Types are the kind of crap you will store in variables. Types define the details of those values. So for instance, a shoe is a real-world example of a type. When I say shoe to you, you kind of get a mental picture of what a shoe is, right? If I put 5 objects out here on the desk, you would be able to look at each of those 5 objects and tell me whether that is a shoe or not. Correct? Even though shoes come in all sorts of different shapes and sizes. We'd be able to look at it and say, yeah, that guy's a shoe. Not a shoe. Right? Because we know what a shoe type thing looks like. Types are the same thing. Okay? So when we define a type, well, in our modern languages, there are types built into the language, and then there are also types that we can write ourselves. We'll be dealing with both of those in this course. Initially, we'll be dealing with the ones built in. Then I'll really scare you. So in any case, there are types built into the language for letting us do normal Java problem-solving stuff. A lot of it has to do with math stuff. Like, for instance, we might want to store a number. Correct? Yeah, that would make sense to us. Like, if we need to remember something, things that we need to remember in real life, we might have to remember a number. Okay, the price of something, maybe. Okay? Other things we might need to remember is a character, char, things like that. Okay, so we can kind of come up with maybe a little list of things that probably were built into the language because there seem to be common things to remember, right? Then we have things that are beyond the norm, things that some of us know about, other people don't. Okay, so for instance, if you build cars, you work on cars, there are objects, there are types of things in cars that some of us won't know what you're talking about, right? We know that they exist, but somebody might not know what a carburetor type item is. So if I put 5 objects out here on the desk and I told you to say, is this a carburetor? Is this a carburetor? Is this... We likely wouldn't all get that right. We could probably put some stuff out there that looks automobile-y, and some of us might think, oh, okay, that might be a carburetor, and it's not. Get where I'm going with this? Okay, so there's the generic stuff, and then there's kind of more specialized stuff. And then there's the stuff we invent on our own moving forward. All right, so a type is the details about what a value is. So for right now, I want us to think about our types as things like a shoe, where it's pretty much common knowledge what a shoe is. All right. So again, for variables, syntax is you put the type first, followed by the variable name. Whatever you want to name the variable probably should be something expressive. So for instance, if you are storing in a container in your head your name, maybe you name that variable my name. Okay? So variable names should be expressive. As an example, your name might be stored in a variable called my name rather than a variable called var or called Bob. You know. So if you have a container you bought from Target, you put a piece of duct tape on it, you write Bob on there, and only you know that you actually put your name in that bucket. When somebody else goes to try to find out what your name is and they're searching through the buckets you put under your bed and they see a box named Bob, does that give them a whole lot of information about what's in the box? No. But if you put tax returns on the box, this time of year you avoid. Okay. Get what I'm saying? And I really like connecting these things to real life problems because it's the same thing. Okay? So if you're keeping your tax return every year, you put it in a box, you label it tax returns, so that next time you need to go find your old tax returns, you pull out a box, you see, this box is labeled tax returns. Okay? But if you put your tax returns in a box labeled thumbtacks, all of a sudden you have to remember that mapping, right? It's like, where are my tax returns? Oh, they're in the box called thumbtacks. That's where you can find them. Eventually, you're going to forget that. Okay, so variable names should be expressive for your own sanity. Java doesn't care what you name the variable names. It has some rules, like they have to start with a letter, or they can't have spaces in them, stuff like that. But Java doesn't care what you name your variables, but I'm suggesting you name your variable something meaningful to what they're holding. All right. Now, a few minutes ago, I mentioned that there are really two types in Java, two global types. One is the types that are built into the language, and the other one is the types that we create ourselves. Okay? And there's actually kind of types that are built into the language that don't fit into this first category. We'll talk about those, but let me lie to you at least for a little bit. Okay, so we have something called primitive types. Okay? The primitive types are basic types built into the language that are that's spelled correctly, that are only capable of holding a value. Okay, now one thing I like doing is I give you these little mantras. I'll ask the same question over and over again. So, for instance, when I ask you what a primitive type is, you should be able to say they're basic types built into the language that are only capable of holding a value. Eventually, you might shorten that down to, they're only capable of holding a value. They have a very limited ability. Primitive types have a limited ability. That is, they can only hold a value. Later on, we're going to learn about the other side of the coin, which are object types. And they can hold 0 or more values and then also potentially do more. Okay? So they're the superheroes. Okay? They're complex animals that can do a whole bunch of cool stuff. Primitive types are boring but necessary. Okay? These are things that are built into the language, but all they can do is hold one value. That's what they do. They hold a value. That's good enough a lot of times, right? Okay, so we're going to talk about primitive types first, but this is what they are. Basic types built into the language that can only hold a value. So let's look at the primitive types. So, primitive types in Java. Let's go ahead and list them out first. We have byte, short, int, long, char, float, double, and Boolean. Okay, these are the primitive types in Java. Primitive types in C. Byte, short, int, long, char, float, double. That's it. Primitive types in C++. Byte, short, int, long, char, float, double, bool, all caps. B-O-O-L. Ooh. Really deviated there, right? Primitive types in C#. Byte, short, int, long, char, float, double, bool, all lowercase. Okay. Primitive types in Objective-C. Byte, short, int, long, char, float, double, bool, all caps. Just like C++. Make sense? Okay. Objective-C also throws a little curveball there with the values that Booleans hold. Booleans hold true and false values. Well, in Objective-C, it's yes and no. But true and false also works. Okay. So, I really want to drive home here this idea that programming is programming. The language doesn't matter. I've probably forgotten more languages. It's all the same crap. If you haven't written something in a while, you sit down, you figure out what you're saying. And we used this example last time. A lot of you speak, English isn't your first language, or at least you speak other languages, right? And one of the things you do when you're with your friends is you tend to speak your home language so you don't get rusty, right? I mean, I'm assuming I hear students do that. My home language is English, so I'm from Kentucky. so we speak bad English. But for those of you who are from other countries, when you are with friends who speak the same language, you probably commonly speak in your home language so that you don't get rusty. That's comfortable for you, right? And one of the reasons you come over to the United States to learn is you're forced to learn English, right? And by speaking English in classes and hearing English, you get better at it. Okay, so now you become bilingual or trilingual or something like that, and you have a real skill set that makes you valuable. Because I don't know Urdu and some of these other languages. So now you know my language and I don't know yours. You got to step up. Okay, so the punchline here is programming languages are very similar. We get rusty. If I haven't written C code in a while, I hunt and peck for a few minutes, and then it kind of comes back, and then you're off to the races again. Okay, but what I really want you to see here, just through that little example we just gave, that these languages are really similar. Okay, because they're all based off the same parent language, C. So the primitives were really defined up here. Then they were slightly changed, if anything, down here. All right. So let's talk about each of these. A byte holds whole integers. A short holds whole integers. An int holds whole integers. A long holds whole integers. A char holds whole integers. A Boolean holds whole integers. A float holds integers with decimal points. Or we can say decimal point values. That'll take up less space. A double holds decimal point values. We have a lot of crap in this list that all do the same stuff. So what do we have? We have 1, 2, 3, 4, 5, 6 different ways of holding whole integers. Well, let's get this a little. Let's narrow this down a little bit. Bytes hold positive and negative whole integers. That's a little better now, right? Shorts hold positive, negative whole integers. Ints, positive, negative whole integers. Long, positive and negative whole integers. Chars, positive whole integers. Only. Yeah, we're gonna keep passing through these several times till we realize why we have all this crap. Booleans, positive whole integers. Floats and doubles, positive and negative decimal point. All right, so we've clarified a little bit, but we're still all over the place here, right? How many of you are familiar with the Y2K bug? Okay, what is that? What's the Y2K bug? Yeah, if you want.
Oh, okay. When the year turned from 1999 to 2000, the year 2000, they were afraid that all the computers weren't going to be able to basically handle the turn of the century, I believe it was, and everybody had to stay up and tech and whatnot, and nothing happened.
Okay. Do you know why? Why were they concerned that the computers weren't going to be able to handle it?
I forgot.
Okay. So, year 2000, when it went from 1999 to 2000, they were concerned that computers are going to crash. Why? Because we've gotten pretty used to rating dates like, so for instance, January 1st, 1999 would be 1/1/99. Well, January 1st, 2000 is 1100. Well, is that January 1st, 2000 or is that January 1st, 1900? So we really needed to have either 1900 or 2000. There's a problem. The computer software that was written had been written for many years before that. And so most of the software was probably written in C, maybe some of it in C++. And we had a problem with technology back then. What's the oldest computer you can remember? What's the minimal amount of memory that you had in any of your computers that you remember?
Hard disk.
Not hard disk, RAM. You can go hard disk too. They'll both tell the same story. Huh?
1 megabyte.
1 megabyte? You remember 1 megabyte of RAM? Okay.
What did Apple IIc have? I can't remember.
Apple IIc maybe had either 128 or 256K. Anybody? I mean, for most of the undergrad and graduate generation today, not of traditional age students, the smallest amount of memory they've seen is maybe a gigabyte. 768 megabytes, maybe. A famous guy one time had a quote that you'll never need more than 32K of memory. Anybody know who that was? Bill Gates, Microsoft guy. You'll never need more than 32 kilobytes of memory. Anything over that's overkill. Okay, how much memory do your computers have in it today? 8 gigabytes. Anybody have 16 gigabytes in any of their computers? I think this computer has 16 in it.
I was going to ask, how many do you have?
Yeah, so this is a quad core i7, Retina screen, 16 gigabytes of RAM. I think I can put it up to 32 if I wanted to. You don't need that much RAM. So 8 gigabytes. Anybody have 4 gigabytes? 4 gigabytes? How much do you think it would cost to upgrade your machine from 4 to 8? You're guessing. 35 bucks?
If it's DDR3.
Yeah. Not expensive is the punchline, right? Relatively inexpensive to double your RAM, as long as your computer can handle it. Okay? This is a far cry from what it used to be. In 1996, I had a computer with 8 megabytes of RAM in it, and I wanted to double the RAM to 16 megabytes of RAM. So I got a 8 megabyte RAM upgrade chip. How much do you think that 8 megabytes cost me? $1,000. $1,000 for 8 megabytes of memory in 1996. Memory was very expensive. Very expensive. Back then, same time period, this is why I said you could have used hard disk size as well. That computer came with a 420 megabyte hard drive. I also upgraded the hard drive. I put a second hard drive in that was like 540 megabytes. That cost another $1,000. If you want to go over and pay retail today, you can run over to Best Buy right now and probably buy a 2 or a 3 terabyte hard drive for $100. Right? That's retail. If you're willing to wait a couple days, jump on Newegg or Amazon or something like that, and you can probably get that same drive for 60, 70. Done. $1,000 for a drive that's a fraction of the size of our drives today. Memory was really, really, really expensive. Therefore, most machines did not have very much memory. Make sense? If something's really expensive and you want to be able to sell it, you can't put too much of it in there. That's why our cars aren't made of gold. Car dealerships would go under, right? That's why they keep making our cars out of, less. Even you look at cars even today compared to 20 years ago, 25 years ago. Back then, cars were a lot heavier duty. My buddy in high school had a Ford Bronco, which I guess they're bringing back. They're bringing the Broncos back, and this thing had to be made of iron. We one time hit a deer. And we were stupid high school kids driving too fast out in the country. We hit a deer at full speed. It looked like nothing happened to this car. If you would have hit a deer in a car today, airbags would have deployed. You would have had the crumple factor in the front.
Probably totaled out.
Right. I mean, his car only got like 6 miles per gallon, but it was strong. I think he bruised his elbow just from the impact. The rest of the car was fine. But in any case, we build things so that they are cost effective. Correct? That's why our cars today aren't made of gold. Gold is too expensive. Okay, we make them out of aluminum or recycled material, or whatever it is, right? Okay, so in the early days of computers, when memory was very expensive, they came with low amounts of memory in them. Therefore, as a programmer, we had to be a good steward of that memory. We couldn't write software that just used up all the memory. So we had to be very careful about how much memory we used when we wrote our program. So at some point in many different software packages, if they were written in before a certain time, they may have decided we're going to represent years as 2 digits instead of 4, because it takes less space to hold. Does that make sense? They were doing it for a good reason, but it came back to bite them. At the time they wrote it, maybe it was 1960 or 1970 that they wrote it. So it wasn't going to be a problem for 30 years. At that point in time, they probably just assumed, things will be magical in 30 years, right? This software won't be there. Things will just work. We're going to have flying cars, and Mr. Spock will be there, and we all seen Star Trek, right? Or at least know of the Spock joke. I had some undergrad students that never heard, they hadn't heard, well, I think they had heard of Spock, but they didn't know about the Vulcan death pinch. Well, see, he didn't know about it either. That was Spock's move. That's how he knocked people out. Just walk up and pinch them right there. Nobody should get in a fight with Spock. All right. So in any case, they were trying to be good stewards of the memory. So they had to use 2 digits instead of 4, so that they had more memory left over for the other stuff the program was going to do. Well, the year 2000 rolls around, and all of a sudden, wait a minute. We have problems. Because when this rolls over, a lot of software, especially software that does sorting and stuff like that by years, isn't going to be able to tell the difference between 1900 and 2000. And think about things that we're doing invoicing and stuff like that, or totals owed. All of a sudden, the dates are going to be upside down. So all sorts of problems can come from the Y2K issue. All right. Now, so these things, all these different ways of holding positive and negative whole numbers, are left over from a much older era. Okay, an era when C was created as a programming language for making operating systems that provided tools for programmers who were trying to be good stewards of memory. So they gave us lots of different ways of holding whole numbers while paying attention to what is the amount of memory each of these takes. That make sense? So let's look at some of these. Bytes hold positive, negative whole numbers, and these are 8 bits big, or 1 byte big. And just to jump onto a second slide here, just to show you this here. Bits are zeros and ones. That's what a bit is, right? A byte is 8 bits. Now, a 8-bit number is a binary number. So that would be a number like, that's the number 1 in 8 bits. Make sense? The number 2 in 8 bits is that. Now, the way this works, as computer science technology people, we should all know how binary works. So let me explain it to you. This is the ones place, the twos place, the fours place, 8s, 16s, 32s, 64s, 128s. Another way you could write this is this one right here is the 2 to the 0th power place. This is the 2 to the 1st power place, 2 to the 2nd power, 2 to the 3rd, 2 to the 4th, 2 to the 5th, 6th, and 7th. Okay? Now, right off the bat, if you haven't dealt with binary before, this might look foreign. A little foreign to you. The reality is, we know how this numbering system works because we do the exact same thing in decimal. If I put the number 125 here, this is the 100th place, this is the tens place, this is the ones place. Another way you can say it is this is the 10 to the zeros place. This is 10 to the 1 powers place. This is 10 to the 2s place. We know this as 125. It's also 100 times 1 plus 10 times 2 plus 1 times 5, or 125. See how the math worked out? Similarly, up here, this is 0 times 128 plus 0 times 64 plus 0 times 32 plus 0 times 16 plus 0 times 8 plus 0 times 4 plus 1 times 2, which is a 2, plus 0 times 1. So this is the binary representation of the decimal number 2. If I put a 1 there, now it's the binary representation of the decimal number 3. 1 times 2 plus 1 times 1. If I put a 1 there, now it's 7. 1 times 4 plus 1 times 2 plus 1 times 1. Now it's 6. Now it's 4. See how that's working? Okay, so this is an 8-bit number. Now what if these were all ones? Okay, if these are all ones, that would be 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1, or 255. Okay, that is 0 to 255, which is 256 unique numbers. Make sense? 256 unique numbers. Does 256 sound kind of familiar to you? We've had 256 megabytes of memory, 256. Well, our computers are based off of powers of 2. Because everything our computer speaks is machine language, which is zeros and ones, binary. Okay? So, those of you who have a newer laptop that maybe has a solid state hard drive in it. Common sizes for solid state hard drives today is 256 gigabyte solid state drive. 128, 512. There's some expensive 1 terabyte solid state drives out there. They're still fairly cost prohibitive. If you're buying a new machine today, the cutoff is around 512. That's, if you need the space, you're not going to cry yourself to sleep at night by the amount of money you spend on a 512, but you might on the terabyte. Okay, that kind of makes sense? Now, if we go back to the previous slide, notice this guy holds positive and negative numbers though. So these guys are what are known as, I'm going to go ahead and I'm going to replace positive and negative with signed. A signed number. Signed is a geeky way of saying holds positive and negative numbers. Okay? Signed, so on and so forth. Make sense? So a byte is an 8-bit signed whole number. That's what this guy is built to hold. So that means, if we go back to this other slide, this bit right there is not used to represent one of the values of it. Instead, it's used to represent whether it's positive or negative. It holds the sign. That makes sense? Okay? So that means for the actual value of it, only 7 bits are actually used. So that's 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1. So the range of values that fit into 8 bits is, for signed, is negative 128 to positive 127. It's the range of values. If you were in an architecture class, we talk about the carry bit and why one's bigger than the other. But you take the absolute value of both of these, you add them together, get 255. Okay? So in a byte, this holds signed 8-bit numbers. So the smallest value a byte can hold is negative 128. The largest value a byte can hold is positive 127. Now that's not going to allow us to solve all the problems in the world, right? But if we only need to count from 1 to 10, will a byte do the trick? Sure. But if we need to count from 1 to 1,000, byte's not going to cut it. Because it can only hold a number as big as 127. Make sense? All right. Short. It's a signed whole number, 16 bits. Let me just take the extra dash off there because I think it's just going to end up being confusing. Take that one off. Take that one off. Okay, 16 bits hold values in the range of negative 32,768 to positive 32,767. You could also say it's plus or minus 2 to the 15th power. This is plus or minus 2 to the 7th power. 1 less than the number of bits, since one of the bits is used for the sign. Make sense? Okay. So shorts can hold numbers in the range of negative 32,768 to positive 32,000. I said it right, but I wrote it wrong. 32,768 to positive 32,767. It's the range of values it can hold. So could this guy deal with counting between 1 and 1,000? Absolutely. Where byte couldn't, shorts can. Make sense? Because I can hold a value bigger than 1,000 inside of a short. I couldn't hold the value 1,000 inside of a byte. Didn't have the capacity for it. Didn't have enough bits to represent a number that big. An int, 32 bits. So plus or minus 2 to the 31st power. So that's roughly negative 2 billion to positive 2 billion. Looks like I'll have the space. There we go. I start losing my precision as we get up higher. I just didn't want to show off. I know all the digits. Okay, a lot of you wouldn't have remembered this one. All right. Long. 64 bits. Plus or minus 2 to the 63rd. Negative big num to positive big num. Starting to see where we're going with this? Okay, so all of these, byte, short, int, long, are all built for holding the same kinds of values. But the capacity of it changes. So a long will take up 64 bits of memory, where a byte only takes up 8. Okay, and just to kind of put this into perspective, because in technology we have a lot of buzzwords. And what I have found among students is, shockingly, they don't know the difference between bits and bytes and megabytes and gigabytes and gigabits and megabits and all those things. And I'm willing to bet a lot of you in this room are in that same boat. Okay, so we're going to talk about them. Here, let me try to trick you first. It's one of my games I like. How many of you know how fast your internet speed is at home? Slow?
Yes.
2 megabits?
Bits. 16 megabits.
16 megabits?
Yeah, bits. No.
Bits, okay. The rest of you just don't know, you're just not participating. Okay? Rule number 1. As a technologist, you should absolutely know everything about your technology. Okay? So if you don't know what the speed of your internet is right now, figure it out before next week. Okay? It's important, you should know that. But more importantly, you should also know what it means. Okay? These numbers get thrown around. Okay? 16 megabit. Sounds like you know. You know what the deal is. Okay? You said 2 megabit, I think you know too. But what's the difference between 16 megabit and 16 megabyte per second? Okay? These get thrown around. Sometimes people just shorten and say, well, I got 16 meg. 16 meg. Right? Okay? So let's talk about, we're gonna create a couple of I'll look at these awesome design skills. Hold on, is that still, yeah, good. Okay, so we have 1 bit. That's a 0 or a 1. 1 byte equals 8 bits. 1 kilobit, small b, 1 kilobit is 1,024 bits. A lot of times it's a bigger K, but the most important thing is the B. 1 kilobyte, big B, is 1,024 bytes. 1 megabit is equal to 1,024 kilobits. 1 megabyte is equal to 1,024 kilobytes. 1 gigabit is equal to 1,024 megabits. 1 gigabyte is equal to 1,024 megabytes. 1 terabit is equal to 1,024 gigabits. 1 terabyte is equal to 1,024 gigabytes. And we can go, that's far enough for the numbers we use today. And we start getting into exabytes and stuff like that. So trust me, it keeps going, but are we starting to see a pretty solid pattern here? The next guy on the list is going to be 1,024 of these guys. Okay? 1,024, by the way, is a power of 2. All right. So, bits versus bytes. Let's do a little math here. So you said you have a 16 megabit per second internet connection. Okay. Now, when somebody asks you how fast you were downloading something off the internet, things that go through our mind. Historically, you might have thought about download speeds in terms of kilobytes. Okay, now maybe we start thinking about it in terms of megabytes. Our internet speeds have gotten fast enough where it's not uncommon for us to see us downloading something at 1.3 megabytes, big B, per second, right? So what is his theoretical maximum speed? Well, I'm going to do the long way here, but then I'll show you the shorthand. So if you have (16 megabit per second, and sometimes this is advertised as capital M, but the B is the important part. Low B. Low B means bits, not bytes. Okay? So 16 megabits per second internet, and that's your download speed. Your upload's probably 3 or less, be my guess. Doesn't matter. The bottom line is you have asynchronous internet because they don't want you running servers out of your house. But this is the one we care about, because we only use our upload for requesting web pages and stuff. The downloads are download speed. We care about that. Okay, so 16 megabits per second. Well, first thing is 16 megabits per second is actually that many kilobits per second, which is actually that many bits per second, which is actually that many bytes per second, right? Which is actually kilobytes, megabytes. All right? Or we could just, yeah, I'll say it here in a second. Or we could just say this. Megabits to megabytes is divided by 8. So your internet connection is capable of a maximum speed of 2 megabytes per second. Okay? So if you've ever seen your internet download faster than 2 megabytes per second, then it's not 16 megabits per second. Okay? So back to your question, this is megabits per second, 16. By multiplying that by 1024, I get to kilobits per second. That's from this chart here. I went from megabits, right here, to kilobits.
Okay.
Then I multiply by another 1024 to get to bits. So multiplied it once to kilobits, multiplied it again to get to bits.
Okay.
Then I divided it by 8 to get over to the byte column.
Yeah, okay.
Okay? Then I divided by 1024 to get to kilobytes. Then I divided by 1024 to get to megabytes. Or you can just say, if I'm already in megabits, why can't I just divide that by 8 to get to megabytes? Make sense? That was the shortcut. All right, so yours is 16 megabits per second. Perfectly acceptable internet. By today's standard, actually, if you followed the news this last week, you don't even have broadband anymore. There was a story, for those of you who follow me on Facebook, I post a lot of tech stories on there. There was a story, the FCC passed a law. I think the minimum speed for it to be considered broadband now is 24 megabits per second. Yeah, you barely have internet, is what I'm saying. And I don't even know what her slow means. Okay? My house, I have 100 megabits per second. So divide that by 8, so I can, at a maximum, I can download 12.5 megabytes per second. Now, realistically, do we get 12 point? Will most sites be able to deliver me stuff at 12.5 megabytes per second? No. Why do I need a fast internet connection? If I'm doing a lot of stuff in the house, if I'm watching Netflix, okay, and my wife is downloading a file, and I have a computer that's playing a video game. When you have a whole bunch of internet activities going on at once, each one of those is taking up some bandwidth. So I have 100 megabits to share across all my activities. Make sense? Now, is 100 still overkill? Probably. But I do quite a bit of server stuff, but I could probably get by on less than 100. But why should you? Why should I? You guys were impressed. Some people show up with a gold car. I show up with 100 megabit per second internet.
Can I ask you another question?
Sure.
How much is your bit?
Not very much. I think I pay, for my internet, I think I pay $65 a month. I've lived here in this area for 8 years, and I have Time Warner Cable, when they were first bringing out their wideband internet, I was working, one of my companies did an app for them. We did some internal stuff, and they had me as a beta tester. So I was running speed tests and stuff like that for them. So I was acting as their end user before the stuff was out. So I'm kind of grandfathered into like this, kind of like the deal people like Best Buy get for unlimited data on their cell phones, that kind of thing. So yeah, I won't be leaving. For instance, I used to have Time Warner Cable for TV, and I don't. I have Uverse for TV now, but I'm not giving up my internet. Because the fastest you can get from Uverse is maybe 18 megabits per second, and it's because it's a different technology. DSL just has speed limitations because of how it works. In the future, we'll probably all go towards fiber. Google's starting to release gigabit internet in some select cities by running fiber all over the place. That's really where the future will probably be. We've kind of maxed out what we can do over the old POTS network, which is the copper wires for the telephone. Plain old telephone service is what POTS stands for. If you take the networking class with me, we talk about that crap. So we really have kind of maxed out what we're doing over copper telephone lines now. Coaxial cable networks, since some of them are fiber throughout in some parts, they have more bandwidth. That's why they're able to offer things like high definition television and stuff like that. But we're pretty quickly hitting the max on those too. I don't think we're going to go much more than maybe we'll hit 200 megabit per second. Maybe. But that would be really hard to hold up, especially when you're fighting with, over the next 3 or 4 years, they're going to be trying to get 4K television content out. And that's something we talk about in the networking class. I mean, I don't think people recognize how difficult that problem is. So the punchline is you get to take the networking class if you want the real story behind it. The what is it, 540? I teach it, whatever the number is. If I were you, I would not buy a 4K TV anytime soon. There's nothing wrong with a TV, but why spend 4 times the price for something that has no content for it? Buy a 4K TV in 3 years when 4K content is available at a third the price of what they are today. Buy a nice 1080p TV. There's barely enough content for that. Get a good one of those. And then buy a laptop or something. So, yeah, 4K, just like the 3D TVs. Technology never really took off. We'll see. There's some technology coming out. CES just had some cool stuff where goggleless 3D stuff. I think that could be cool. But if you're sitting on your couch, you have to put this headgear on and stuff like that. It's kind of gimmicky, I think. But in any case, don't buy a 4K. Technology's fine, but half the time, 99% of the time, the maximum you'll be running your TV at is 1080p, 1920 by 1080. A fourth of what it's capable of. Save your money. Buy something else. All right. So in any case, that's the punchline with the megabits to megabytes and kilobits and bytes and bits and all that crap. Okay? And really all this at its core comes down to computer science and IT. Because at the end of the day, machines talk zeros and ones. And these structures, these bits and bytes and stuff like that, are more for us, for organizing these into larger chunks. Okay? In computer architecture, we call 2 bytes a word. Okay? We call 4 bytes a double word. It's just our own naming conventions for these things. Okay? So, whether you call it a byte or you call it 8 bits, it's 8 zeros and ones. Deal. That's what it is. Okay, so back over here. So a byte, signed whole numbers, 8 bits, negative 128 to positive 127. Short can hold negative 32,768 to positive 32,767. An int can hold negative 2 billion to positive 2 billion, and a long can hold a negative really big number to a negative really small number to a positive really big number. Make sense? Really small? Haha. Negative 10 is smaller than negative 9. All right. Now, chars. These guys hold whole integers. Now, I'll tell you that char is short for character. Okay, so these are all a whole bunch of ways for storing numbers. This guy down here is for storing characters, like an A, or a B, or question mark, or comma. Those are characters. Make sense? But I've advertised them as storing positive, only positive, whole numbers. These guys are 16 bits. That's 0 to 65,535. That's the range of numbers that fit inside of a char. 0 to 65,535. Okay, now here's why. How many of you have heard of ASCII? What is ASCII?
Keyboard alphabet.
Okay.
For all languages.
You said it doesn't support all languages? Okay. So ASCII, first of all, stands for American Standard Code for Information Interchange. Did I spell it all right the first time? American Standard Code. Woot. All right. So ASCII is American Standard Code for Information Interchange. It is an 8-bit code. Holds the values between 0 and 255. So there are 256 unique characters in the ASCII character set. All right, now as you pointed out, it doesn't support all languages. Well, American Standard Code for Information Interchange was probably made by Americans, right? Why should we support other people's crap, right? We can't even use, it actually gets funnier than that. Not only, does it not support other languages, we don't have 256 unique characters in our language. So actually, some of the ASCII codes support things like playing cards and smiley faces. So if you've ever opened up a file, like a notepad or something like that was formatted funny, or opened up a .exe file in Notepad, sometimes you'll see like smiley faces in there, or the 3 of clubs, there's a little icon looking thing. It's just because it's that text editor is trying to take a binary program and make it look. It's every 8 bits. It's trying to figure out which ASCII symbol is this supposed to be, and showing it to you. Okay, that's how lazy Americans are. Instead of using the extra characters to maybe put in some other common characters from other languages, we put smiley faces. It's actually quite funny. All right, but that's ASCII. An older language like C and C++ only supported ASCII. Okay, anybody know what replaced ASCII? Unicode. So now we have something called Unicode. And that stands for something, but we'll just keep that as an exercise for the reader. This is a 16-bit character set. So that's 0 to 65,535, or a total of 65,536 unique chars. All right. Probably doesn't support every language on Earth, but supports a lot. All right. So this is meant to be, actually it might just stand for universal code, now that I think about it. But whatever. This is the upgrade to ASCII to support multiple languages. Java and C# both are default to Unicode. Okay? So the reason our char, where are we going here? This guy, holds 16-bit positive integers is because it holds the number 0 to 65,535. Each of these integers maps to a character on the Unicode character set. So the character at position 0 in the set is this. The character at position 1 in the set is this. The character at position 2 in the set is this. So on and so forth. That make sense? There's 65,536 unique characters. Each one is indexed by a number because computers like holding numbers. That makes sense? So we have this character set for doing that mapping between the two. All right, chars make sense? All right, floats. A float is a positive, negative decimal point value. These guys are 32 bits. The reality is they're actually 32 on the front by 16 on the after the decimal point, I believe, for Java. Just, I guess, deal. Pretty close. Where double is 64 bits on the front and 16 on the back. So a float is a decimal point version of an int. A double is a decimal point version of a long. Make sense? So it holds floating point numbers. Now,
Can you say that again?
a float is the decimal point version of an int. So an int is a 32-bit number that holds just positive and negative whole numbers. Floats is a float is a 32-bit number also, but it also holds 16 bits worth of decimal point value. It can hold 3.14, for instance, in a float, but you can't hold 3.14 in an int. The 0.14 would get cut off. Okay, so a float is kind of like an int for decimal point numbers. A double is like a long for decimal point numbers. All right, so the biggest value we can hold as a whole number in Java without getting more creative, biggest number built into the language, is whatever the biggest number that a long holds, which is positive 2 to the 63rd power. Big number, right? Okay. Now, it's not an infinite number. So that means if we did need to hold numbers bigger than that, there are some options beyond these primitive types. But that's what a primitive type can give us. That right there. Make sense? Okay. Similarly, a double can give us up to a certain point, but eventually you run out of precision there as well. 64 bits is not unlimited. It's big, but it's not infinite. Make sense?
Excuse me.
Yep.
While most processors today support the 64-bit instructions, so what's the point of using the bytes and the shorts and the other two today?
Okay, now I want all of you to remember that this was his fault. Because this is a tangent. I'll try to be brief. What does 64-bit processor mean?
Support 64-bit instruction.
Okay, 64-bit sized instruction. Okay, that's different than a 64-bit number. An instruction is a chunk. So the instruction is stored in 64 bits, zeros and ones, right? Okay, so as our processors get bigger and faster and all that stuff, we've gone from 32-bit processors to 64-bit processors, because we talked about this last time, I believe. We talked about CPUs, right? And the magic tricks they can do, that kind of stuff, okay? Well, you go back to our really old CPUs, and they could do this many magic tricks. And as the CPU kept getting newer and newer and faster, it could do more and more and more and more magic tricks. And eventually, we run out of the number of magic tricks that can fit in a 32-bit space. Now you have to go to a jump to a 64-bit space to give us more magic tricks. Okay, there isn't anything between. One more bit, one more power of 2 jumped us to 64. That's what I'm saying. You need to stay in powers of 2. So early 64-bit processors were substantially less capable than modern 64-bit processors, which will be less capable than 64-bit processors 3 or 4 years from now. Because we keep adding instructions, magic tricks on, that allow that processor to do more powerful things. Does that kind of make sense? But this actually flows through to a lot of different stuff. A good example would be, and actually I think I asked, anybody in here have more than 8 gigabytes of RAM in their computer? Okay, well, one thing you would have known, or you would have noticed, if you tried to put 8 gigabytes of RAM, probably the best example would have been Windows Vista. When Windows Vista was out, the stock version of Windows Vista was a 32-bit operating system. Okay? They had a 64-bit version, but a lot of software wasn't prepared for 64 bits. So most people got the 32-bit version of Vista. Okay? People complained about Vista. It was fine. Microsoft is the big target, so they had to be annoying with all the security stuff to make the thing not crash all the time. Windows 7 was Vista without all the annoying crap. They just made some decisions for you behind the scenes. It wasn't that the operating system was crap. But in any case, you would get your 32-bit version of Vista installed in your computer, Windows Vista, and let's say you had 16 gigabytes of RAM. How much would show up?
3.7.
Yeah, it would be 3.5 is what would actually show up. Functionally, it was 3.7 because they would grab 200 megabytes for 200 and change, 212 megabytes, I think, for virtual memory. But you bought 8 or 16 gigabytes of RAM. What the heck? 32-bit memory manager. 32-bit memory manager. Biggest it could hold, because of the way the memory manager worked, was 4 gigabytes, 3.5 addressable, because of their overhead for the, they had restricted memory specifically for the operating system, reserved about a half a gigabyte. So you had a lot of people complaining about that. Now on the flip side, you've been able to put 16 or 32 megabyte or 32 gigabytes of RAM in the Mac for a long time. And it's not because the Mac is just natively better. Okay? It's that they rewrote their memory models, a 64-bit. Well, actually, I say they rewrote it. The operating system they stole, which is OpenBSD, when they jumped to Mac OS X, when they went from OS 9, which was garbage, to OS X, which was a brand new operating system that was, they went out, they took OpenBSD, which is a Unix operating system, put a fancy front end on it, and called it Mac OS X. So they made it look Apple-y, made it look pretty, right? But it's really a Unix operating system, which had a 64-bit memory manager built into it. It was able to support up to, I think now it can support up to 2 terabytes of RAM. But bottom line is you didn't have those problems with it, not because it was better, but just because it was more updated for how much memory it took, what size of number it used to index through RAM. RAM is just a whole bunch of buckets. Something we're going to talk about in here is an array. Okay, not in this class, but probably 3 or 4 classes down the road. We'll talk about something called arrays. And memory really works like arrays, where it's a single stick of RAM, and think about it as a whole bunch of little tiny cubby holes. Each one's capable of holding some stuff, some memory. Okay? Well, the size of the integer, the size of the number you use to index those cubby holes, this is cubby hole 0, cubby hole 1, 2, 3, 4, 5. If the size of that is too small, you limited yourself on the number of cubby holes. Make sense? And typically most operating systems, each cubby hole has a fixed size that it can hold. How much data? Maybe it's 4 bytes per cubby hole, let's say. Just using this as a quick little example. Don't worry about this too much. But that means that you take 4 bytes times the maximum size of cubby holes that you can have. If you're indexing based on shorts, you can have 32,000 cubby holes. And you multiply that by bytes, well, now you have a limitation. That's the maximum number of bytes that you can store in that memory because you can only index that many cubby holes. If you double your size, so instead of being a short, maybe you're indexing on ints, now you have 2 billion cubby holes you can index. Well, maybe things are a little bit better now. You can store more stuff. Actually, it's 4 billion. 4 billion cubby holes because we don't need to index negative ones. So if we are using a 32-bit number for indexing, we can use all 32 bits, 0 to 4 billion. Where if we were indexing on a 16-bit number, we would get 0 to 65,535. So 65,535 times, let's say it was 4 bytes big. That's 262,140 bytes. Divided by 1,024, that's megabytes. You're starting to see some limitation. So 256 megabytes if we have a 4-byte per cubbyhole limit and we're using a 32-bit number or a 16-bit number. If we're using a 32-bit number, let's see, let's just do 2 to the 32nd powers. There's your 4 billion number, right? That's exact. That's what I was saying when I said 4 billion, that number. So that's our 4 billion number. So that's the number of cubbyholes we can index, that guy. Okay, and we're going to multiply that by 4 bytes. That gets us there. Then we'll divide that by 1024. That gets us to megabytes. By 1024, that gets us to gigabytes. See the jump? Just by 1 power of 2. Okay, so depending on how they implemented the memory manager, how many cubby holes you can index makes a big difference on how much memory, maximum memory you can have. Does that make sense? So same thing goes into hard drive for the file system, whether it's 16 or 32-bit file systems. Earlier, when Windows 95 first came out, even if you had a 4 gigabyte hard drive, the biggest single partition you could make is 2.1 gigabytes. So you could have a 4 gigabyte hard drive, but you had to split it into two 2 gigabyte partitions because the memory manager couldn't index on hard drives. They're called blocks. Although, and for memory, I called them cubby holes. They're really called frames. Okay, but same thing. They work the same way. How many cubby holes can I index? Make sense? So same crap across the board. Everything comes back to the Y2K problem. You know, you can say, well, why don't we just do everything as long, as 64 bits? Why didn't they just use 64 bits a while ago? Well, first of all, we didn't have the memory to do it, right? If we only have 32 kilobytes of memory, okay, so 32 kilobytes, that's 32 times 8. That's 256 kilobits, right? Well, weren't you saying you had a Apple that had 256 kilobytes of memory? That's probably what it was, right? So that means on that machine you could have only held 32 total longs. That's assuming your operating system had a size of 0. You can remember 32 things if they were size 64 bits. Now, a lot of us might sit here and say, well, I can't really remember 32 things anyways. So, okay. But realistically, that doesn't seem like a whole lot of stuff. Computers seem more complex than that, right? So we'd start running into problems pretty quick, is the punchline there. All right, so that whole 64, 32, 16-bit stuff, it transcends, it goes a lot deeper into the things, and it also is not necessarily consistent. You can have what they're calling a 32-bit operating system with a 64-bit memory manager, which is what Apple was for a while. Now most of them are 64-bit on most sides. Actually, NTFS has been 64-bit for a while. Their file system. FAT32 was 32-bit. So actually NTFS on Windows was probably their first jump to 64 bits because that was their new technology for their file system. They probably didn't jump the OS, the core OS, to 64 bits until Intel failed with their Itanium processor, their 64-bit processor, and then AMD started making 64-bit processors pretty consistently, and finally Intel came back with 64-bit processors. So probably right around the Core 2 Duo, be my guess. When the Core 2 Duo processor came out is probably about when Microsoft really seriously thought we need to go full 64-bit across the board, which then had other problems. For instance, I think it's fixed now, but for those of you who started running 64-bit operating systems relatively early, you couldn't run Flash. You had to install a second browser that was the 32-bit version of the browser for the Flash plugin to work, because there wasn't a 64-bit version of the Flash plugin. So it wouldn't work with the 64-bit version of your browser. So it's you have to have a lot of people playing the same game in order for everything to line up to make a jump like that. Just having a 64-bit processor. In fact, you might even be able to argue that one of the reasons that AMD, as a processor company, failed. I think they're actually closing their processor division here pretty soon. But whether they close their doors soon or declare bankruptcy, whatever, we all knew it was coming. They've lost the war to Intel. But for a long time, AMD was really popular. Probably the reason that they took a gamble. They took a gamble of going multi-core ahead of Intel and also going 64 bits. And what they did is they jumped to 64 before everything else was ready to be 64. So their processes were actually running slower than the equivalent chip from Intel because they were all having to run in compatibility mode for 32-bit code. Does that make sense? So they bet big and were probably really almost a decade ahead of themselves in terms of what it actually came to be. And it wasn't because 64-bit technology was really a stretch. It was we had to get all of these different partners on board. Internet breaks if we don't have Flash for a lot of sites, right? Can't really have a 64-bit operating system with a 64-bit browser if you can't run Flash content, right? So a lot of things you don't think about you have to have all your ducks in a row in order for it to be worthwhile. Because typically a consumer, and this kind of gets back to what we were saying before, if we're using product X and product Y comes out and product Y is really a lot better, maybe it's worth the learning curve. But if product Y comes out and it's just a little bit better, or we would have no perceived benefit from it, why should we switch? So even though 64-bit versions of these operating systems were out, if we would have no perceived benefit from it, why not just let our stuff keep working rather than go and switch over to 64-bit and figure out what broke? That makes sense? So it's but I think we're in we're at the point now where I think 64-bit has moved into kind of its comfort zone. So we'll be fine there. I don't know, probably in 5 or 6 years they'll be talking about 128-bit something or other, and whatever. Okay, let's see here. So those are floats and doubles. Boolean is a positive whole integer. The reality is they are stored as unsigned bytes in Java. Not because that's efficient, but because Booleans are implemented in terms of the other primitive types. And what I mean by that is the reality is behind the scenes, a Boolean is a 0 or a 1. It's a 0 or a 1. Okay? So false, true. 0 or 1. Okay? And we'll talk about Boolean expressions here after our break. So that's the values that it holds at the core. So in the old language C, a Boolean true was a 0. A Boolean false was considered to be anything non-0. It was usually a 1, but anything not 0 was considered to be false. All right, now having said that, the size of value that we hold 0s or 1s in, will a 0 or 1 fit comfortably inside of 8 bits? It will. It will. Will it fit comfortably inside of a lot smaller value than that? We actually only need 1 bit to store a 0 or 1, right? The reality is because of how our hardware works in our machines, we don't have the capability of storing things at the granular level of 1 bit. It's inefficient to store things in that small of chunk. So we get things called fragmentation. You would have internal fragmentation because, like we used our example earlier about the cubby hole. Let's say your cubby hole was 4 bytes big. and you were only going to store 1 bit in there. Well, 4 bytes is 32 bits, right? So you're only using 1/32 of the storage space in there. Big waste of space. That make sense? So from an operating system designer, from a hardware designer, you have to play that game. What's the smallest piece of data that we are going to allow to be stored? And how much will that cost us in performance? Is it better off to waste a little space internally, but give us more performance externally? There's a balancing act there. In my operating systems classes, we talk about specifically with memory, paging memory management, which is the modern day way of doing it. A page has a size. Earlier I mentioned they're called frames. A page fits inside of a frame. Well, something we have is this idea of internal fragmentation, which is, I just described that. You need to store 1 bit, but you have a bucket capable of holding 32 bits. Rather than getting a smaller bucket, you just toss the 1 bit in there and say, whoop, the rest of it's wasted space. Sometimes we do that, right? When you have your giant thing for your tax returns, you might just throw 1 piece of paper in there. Could hold a lot more than that. Check back in 30 years. There'll be more crap in there. So you might say, okay, well, what if we just make every frame the size of 1 bit? Then we've completely gotten rid of internal fragmentation. No wasted space. You're right. But now to index through memory, to go from this piece of a program to this piece of a program to this piece of a program, we're going to be constantly jumping through different places of memory, which is going to slow everything way down. We'd like to land in a box. So if we're thinking about looking for something and the box is under the bed, we'd rather work on 1 box for a half hour than look at 30 boxes 1 minute at a time. That makes sense? That's kind of the analogy. Yeah.
That goes for the other data types also, right? I mean, like if you're taking an array and you have to use float, but then you're using a double, so then again there's a memory wastage there, or the precision.
Maybe I don't get what you're asking. Does what go for the other primitive types?
Like, float and double.
Okay.
So let's say if you're having an array that you really have to use float.
Okay.
But then you use double because of the extra space there, right?
You mean as a programmer, I might choose to use double?
Yeah.
Well, if you really only needed float, then you probably should have just used float.
But how do you, at what point do you know, like, exactly?
Well, it's a good question. It really depends on how much you know about the data you'll be working with. If you're the programmer and you know you'll never have a value above 100, then you know you can if you know you'll always have values that are greater than 0 but smaller than 100, you know that a byte is completely safe. But what if you don't know the nature of your data? Then maybe you decide, okay, well, I'm going to use longs and hope for the best.
Excuse me.
Yeah.
Normally, which one is advisable?
Okay, so there's advisable and then there's common patterns. Common pattern is for whole numbers, everybody uses an int. If that's not big enough, you use a long. You will rarely see anybody today using shorts. You might still see people using bytes, but not because of the size limitation, but because they're streaming data like video or something, and it's coming in 1 byte at a time. It's just the right data type for what you're getting, not because people are trying to preserve memory. So modernly, people use ints unless that's not big enough, and then they use long.
So does Java throw up an error message or something like that when it's not?
Yeah, if you try to put the number 300 inside of a byte, it'll yell at you. And we'll look at that after break when we actually get into some Java code. So that's on the int side. So common practices on the int side, on the whole number side, would be int, typically, if it's not big enough, use a long. If it's not big enough, then hopefully you're working with a problem that, hopefully you know enough to know that there's other options. We have something called big integer that allow you to deal with arbitrary size numbers. Now, interestingly enough, though, on the floating point side, the common thing is double. You will rarely see people use floats in Java or any modern language.
But even in C#, I think they don't use float much.
Yeah, they don't. They don't. Yeah. Yeah. And it's really a very different mindset to what we've had historically. You know, we go back to that Y2K problem, and we had this situation where memory was at a premium. So we had to be very, very, very good stewards of memory. Today it's not, right? I got 16 gigs of RAM. I'll just make everything a long. Who cares, right? You know, I could store millions and millions of longs. It's not a problem anymore. Our mindset as programmers has changed. And actually, our compilers have improved as well. We'll talk about compilers some more, you know, as the class goes on. But remember, we talked last time that the job of a compiler is to convert a high-level language into a low-level language, right? That's what a compiler does. We had our diagrams up here of like the Java compiler. Java source code goes through the compiler, turns into Java bytecode. So this tool here converts a high-level language to a low-level language. Low-level has a one-to-one relationship with the CPU. High-level has a one-to-many relationship with the CPU. Okay? Well, our compilers have gotten so good today that in many ways they take our bad programming and turn it into more efficient code. So if we use bytes and it can figure out that we never actually put a value, if we use a long and it figures out that we never actually put a value in there greater than 100 and less than negative 50, it'll turn it to a byte. If it can, without a doubt, figure that out for us. Okay, so, but generally speaking, programmers today don't worry about memory. And if you are having to worry about memory, you're probably a pretty advanced programmer and you're working on a project where you know memory is an issue. Make sense?
Yeah.
So, for instance, let's say you're writing games for like Xbox or PlayStation, where every single console has a very fixed amount of memory. They have a lot of memory, but if you're trying to write games that completely take advantage of every last piece of horsepower that machine has, you might start caring about memory a little bit because you want to fill it. You know, you want to have everything awesome on the screen and all this stuff, and you know, then you might start thinking about memory. But I would say it's fairly rare today because you know, we almost think, at least in the United States, we think about memory probably like we think about water. I mean, really. I mean, water is a shortage in a lot of places in the world, but we just keep running water, right? Who cares? We got plenty. Eventually, that'll probably bite us in the butt. I always thought that reminded me. We'll take a break here in a second. But how many of you have seen the movie Waterworld? Kevin Costner? The very opening scene, I always thought this was funny. You know, I guess there was, the whole world was water, so everybody was sailing and stuff like that. Well, he was purifying his own urine to drink on the boat. He's surrounded by billions and billions of gallons of water. If he had the technology to purify his own urine, he can desalinate the ocean waters. Why the heck is he? I don't know why I thought about that. I just think about people peeing sometimes. This is what okay. So let's see. We get a good stopping point. All right, so final punchline there. Booleans, even though they only have to hold zeros and ones, they're actually implemented as bytes because that's kind of our smallest common denominator that we can store. In Java, we think of them as trues and falses. And we'll see that. We're going to be talking about Boolean expressions after break. All right, questions, comments, concerns about any of the crap we just talked about?
I have a question.
Sure.
You said that for CPU are still adding more new tricks and just like operations, but how the interpreter identify this? For example, like Android, the CPU company is still upgrading their CPU. How can
but it's a superset. So when a new CPU comes out, it can do everything the old one did, and then more. So any programs that were compiled under the old model, they were compiled in terms of the old magic tricks. So they're not going to take advantage of the new features of it. But if you go back and recompile it with the new flags for the expanded feature set, there might be some aspects of your program that accomplish the same end game, but maybe accomplish it in a quicker or more efficient way because it utilizes some of the new magic tricks. So it's some of those things. I mean, like, for instance, my first iPhone app I wrote was a dice roller for like Dungeons and Dragons. And I wrote it once, took 10 hours, and I wrote that 8 years ago. I haven't touched it since. Well, there's been a lot of innovation to the CPUs in those machines since. My app still runs, but I haven't touched it. It's compiled for the original iPhone CPU. Now, a dice roller's not doing that much stuff, so it's fine, but that's kind of the point, is those CPUs, when they come out, they're always backwards compatible with the guy before them. They're supersets. All right, anything else? All right, so let's take about 15 minutes, stretch, grab some food, whatever, and we'll circle back here, 8:16, 8:17, something like that.